rather than just assume there is a magnetic field. So in this chapter, we'll talk about the magnetic field due to a current, which means a current can generate a magnetic field, and the force between two parallel currents. Because if you have magnetic field and you have a current, you have a force acting on the wire. And now, if you have two parallel currents, so that this current will generate a B field, then the B field will have a force acting on the wire. And also, this wire will generate a magnetic field, so that there is a force also acting on the other wire. And also, we talk about the Ampere's law, which is also one of the equation in the one of the Maxwell equation, one of the four Maxwell equations. And also we have a solenoid and toroid. Finally, we'll discuss the current coil as a magnetic dipole, which means coil is equivalent to a magnetic dipole. That's why we talk about dipole in the last chapter. So in chapter 23, we learn about the Gauss law for electricity, and actually this one is the Gauss law for magnetism, which is very similar. And in this chapter, we will learn about the Ampere's law, actually without this term in chapter 29, and in chapter 32, we will add this term. This is all called the displacement current. Displacement current. And this is the Faraday's law. We'll learn it in next chapter, chapter 30. And actually, we do need to write the lab report. This is actually based on the Faraday's law. So, so let's talk about the magnetic field due to a current. The magnetic field of the magnitude of the field dB produced at point P at distance r by a current length element ds turn out to be something like this. dB, this is what we call the law of Biot-Savart or Biot-Savart law. Something like a Eastern European name. I've not checked it, but I'm not sure. Biot-Savart law. So actually, for this equation is something like suppose this is a wire with a current I go through it. So for this segment, because this wire may not be a straight line, or even if it is a straight line, ds cross r may not be in the same direction. So we try to separate the wire into infinite small pieces. So ds with the direction same as the current, and r is from this infinite small segment to the point you concern. This is r, and r hat is the unit vector in this direction. So the magnetic field generated by this segment is μ0/4 pi times the current. So the current, if the current is larger, the magnetic field is larger. And ds cross r, which means ds point to something like the upward, and r is something like this. So b is into the page. IDS is the blue arrow, something like that direction. R is here, so ds cross r is something into the page. into the page. So this is the scalar form. So it is mu0 over 4 pi times I ds sine theta r squared. So if we write it as a vector form, sine theta is absorbed by the cross product. And this is the unit vector. Remember, it's a unit vector. So the magnitude of a unit vector is always 1. Otherwise, if it is r, then it is r cubed, so that to cancel the magnitude. So here comes a new constant, mu0. In the electricity, we have epsilon 0. And here we have the permeability. That one is, I forgot the name. I forgot the name. Actually, this is mu0, that is epsilon 0. The two most important constant in the electromagnetism. So mu0 is something like 4 pi times 10 to minus 7 Tesla meter per ampere. Why these two constant is so important? Because in chapter 33, you will know that this is a very important constant, which is known as the speed of light. Speed of light. Speed of light is related to the electricity. It's related to the epsilon 0 and mu0. In chapter 25, you learn the capacitor. So if there are some dielectric, we use copper epsilon 0 rather than epsilon 0. And at that chapter, I told you that copper must be larger than 1. So this is the speed of light in the free space. And actually, mu for magnetic material also larger than mu0, which means that the speed of light in free space is the fastest. The speed of light in other material can only be slower than that. In high school, you may know that C is equal to 3 times 10 to 8 meter per second, and actually it is something like 92458 meter per second. Actually, when you study the relativity, it will tell you to use 2.99 times 10 to minus 10 times 10 to 8 meter per second rather than 3 times 10 to 8. But actually, this is something like a more accurate number for that. It's something like a telephone number. Actually, I remember it in junior 1 until now. So this is the speed of light. And this is a speed of light is a absolute value. It does not relate to the velocity of the reference frame, which is conflict with our intuition. If we have time, I will also talk about the special relativity after chapter 33, which is very interesting. This to assume the speed of light is ultimate constant is one of the assumption in the special relativity. So let's continue. This is mu0. This is mu0. Okay. So we also need to calculate the cross product. And the vector equation and its scalar form known as the law of Biot-Savart. So using the law of Biot-Savart or Biot-Savart law, we can calculate the magnetic field generated by the long straight wire carrying a current I. And actually, the so this is the current. 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 And pointing into the page. So the B field generated by this long straight wire is this. B equals mu I over 2 pi r. And the direction is something like this, which is rotation with respect to the wire. And it follows the right-hand rule because the current is pointing into the page, which means you use the front pointing into the page, and the B field should be rotating clockwise, rotating clockwise, so that the current point into the page. And likewise, for semi-infinite straight wire, the magnitude of the magnetic field is half of it, because the upper side and the lower side should be symmetric. So if it is semi-infinite from 0 to infinity rather than from minus infinity to infinity, the magnetic field generated by a semi-infinite straight wire should be half of this. So here shows how to derive it using the Biot-Savart law. So we know the Biot-Savart law is something like this. And this is the ds. This is the ds. Theta is the angle between ds and r. So we concern the magnetic field at point P. So we cut the infinite long wire into many infinite short elements, and then we integrate them together, and that's it. So according to the symmetry, so the total magnetic field is 2 times the integral from 0 to infinity, because from minus infinity to infinity is symmetric. So we only calculate half of it and multiply by 2. And then we substitute the Biot-Savart law into here. Mu 0 I over 2 pi are constant, so they factor out. Sine theta is a variable related to s, so it cannot be factored out, and also r is related to s. Now we know that r is the distance between this element and the point, and this is theta. And actually this is pi minus theta. Not this one, that one. This one is pi minus theta. This one is pi minus theta. And so this is a Pythagorean theorem, so that we have r squared equal to s squared plus capital R square and take the square root. And also we have sine theta. Sine theta is equal to sine pi minus theta. This is what you learn in the trigonometry. So this is equals to R over capital R over R. So we substitute small r into here. So we have something like this. So here we substitute into these two into here. Then we will have r over this term to the 1.5 power, to the 1.5 power, and we need to calculate this integration. So actually the integration of this one is something like this. You can check it yourself. I don't repeat it here. Actually, I think you still need to use some trigonometry substitution to work it out. Or chain rule? No, not really. Chain rule maybe not okay. Oh, but this integration shouldn't be too difficult. So actually, you have the magnetic field something like this, and you substitute 0 into here, so that s equals infinity into here. I mean, s equals infinity, so that this is 1, this is 1. When you substitute when s tends to infinity, this term is 1. When s is 0, this is 0 over r, so this is 0. And don't try to use many of you in the quiz 2, you see 0 here, and then you minus 0. But actually this is minus 0 square plus 0.15 squared, something like this. So this is not 0 in quiz 2. So don't just look at the 0 at the lower bound and then you write minus 0. You really need to check it. So finally we can get B equals mu 0 I over 2 pi r, which is a very important result. This result will appear again and again in the coming 2 chapters, I think. So up till now, any questions? Sama? Oh. 你的意思是应该反过来吧？跟我的 R 是30。哦，不是啊，我刚才就说不是。这个是 This is a unit vector. This is a unit vector. This is a unit vector. 如果你写这样的话，它就是 R 3次。但是这个是 R hat. This is R hat, so this should be R squared. So for this page, this is the magnitude of the magnetic field at the center of a circular arc of radius r and central angle 是圆心角。 circular angle. So suppose this is part of a circle, and this is the central angle. Then the magnetic field generated by this segment is mu 0I over times phi, which is the central angle in radian. In radian is very important. Don't substitute the central angle in degree and then totally different. And over 4 pi r. Over 4 pi r. So if you use the Biot-Savart law to derive it, it is simpler because when you substitute the Biot-Savart law into here, actually the magnitude of dB is constant, and also the direction is are all the same. So that you have mu 0 4 pi r square, all are constant to s, and also I, and theta is 90 degree, so sine theta is 1. So the remaining stuff is only ds. All the other stuff are constant because it is a circle. So capital R is a constant. So we have this one multiply this one, and actually ds is r times d theta pi. Yeah, you should have learned it in high school. ds equals the radius times the angle. So in this case, r, one of the r cancel, so only r remain, and you integrate d theta pi from 0 to pi from 0 to phi, so it is phi. So actually, the magnetic field generated by a circular arc is can be written like this. So the special case is something like for center of a full circle, which means phi equals 2 pi. Phi equals 2 pi. Then the magnetic field for a full circle is something like mu 0I over 2R. This is the special case for 29.9. Biot-Savart law is something quite important in magnetism, although it is not in the Maxwell equation. Actually, I've checked the Wikipedia. You can really derive the displacement current using the Biot-Savart law, but the derivation is really complicated. Okay. Let me see. So we may finish here because we have 2 sample examples. Let me continue next week.